reminder that when you turn in the lab today, be sure to put the stamped sheet on the front page. Or if it's part of your data, just make a copy of it and put that on the front. So that is just the insurance that you were there and actually did the lab. Yeah.
For future labs, are you going to have us get something stamped and put it on the lab too? Because it's
Yes.
virtual? Okay.
Yes.
Okay. And
Yeah, so you'll just upload that and then put that on the front page. All right, so where we left off last time is we had a curved mirror equation, and we were looking at what we call a positive mirror. And so that's this kind of a mirror here. One, we call it concave, and maybe the way to remember that is it's like crawling into a cave. You know, it's indented rather than poking out at you. And so this concave mirror then allows for certain kinds of images to be formed depending on the distance of the object from the mirror. We can form an image at some other location. And so that's our goal for doing this, is to form an image. And that image will have some kind of strategic value. Okay, so our basic working equations then are 1 over I plus 1 over O equals 1 over F, where O again is the object distance, F is the focal length, measured from the center of the mirror, and I is the associated image distance. Now, your handouts go through all these different cases, and also on the front page of your handout, you've got a derivation of this equation. And on the second page, you have a derivation of this equation, minus I over O. I'm not going to hold you responsible for memorizing the process of deriving it, but I would want you to be able to use this equation and be able to draw the ray diagrams. You won't see that today, though, not on today's quiz, but definitely on the midterm, which is coming up a week from today. And so let's draw a focal length here and look at some different cases. Last time we looked at a situation where the object distance was less than the focal length away. And so I'm going to put that object in here. For this example, I did one last time. I'm going to do another one today. Let's say that the focal length is 10. Normally, we can use centimeters instead of our normal meters for these kinds of processes, because that's more typical of the lengths that we're talking about. And there aren't any unit conversions to do here. If you do everything in centimeters, then your answer comes out in centimeters. And so if, let's say, F is equal to 10, and our object distance is equal to 5, let's just try to draw this in proportion here, where I'm putting the object distance twice as close in. That's our source of light. Then we can calculate the associated image distance. Okay, and so we get that then from 1 over I equals 1 over F minus 1 over O. And I always have people that just say, well, that's the same thing as I equals F minus O. And of course, that is algebraically very, very wrong. So you know that we have to work with the inverses to make this work. And so F here in this case is going to be 1/10. O is going to be 1/5. I'll write that as 2/10, just so that I have the lowest common denominator, so I don't have to pull out my calculator to solve for this. Now, sometimes you'll need your calculator. In the example that I gave last time, a more general example, I needed my calculator. But a lot of times I'll pick numbers so that it's not necessary if you just find the lowest common denominator. You just leave your calculator alone. Or you can still use it, whatever you want. But 1/5 is a bigger number than 1/10, so this will always be negative. So this tells us that I is less than 0. Okay, remember, every time that I am referring to 0 in this section, I will write out the word so we don't confuse that with the object distance. And the book, a lot of times, they'll do things like P and P prime, and who knows which one is which. You can never remember. I and O is the way we have things set up in our labs, too. So I think that's a better way to do it. So 1 over I, then, is going to be negative 1/10. Or now we can flip it. I, then, is equal to minus 10. So I can say that my image should be on the far side of the mirror a distance of 10 centimeters away. So how can I verify the mathematics of this? And also, what's my magnification? Well, my magnification is going to be minus I over O. So in this case, that's going to be minus a negative 10 divided by O, which is 5. So that should give me a plus 2. So in other words, when I draw my ray diagram, I'm going to expect an upright image. The plus means upright. The minus here means virtual, meaning that the light doesn't really come from that location, but it just looks that way to the eye because the eye is extrapolating along straight line paths to the apparent source. And so one ray that we can always draw for this, and Mr. Clark a lot of times will do 3 or 4 rays. I think 2 is enough. In the book, sometimes they'll do 3 or 4. If you want to do more, it's okay. But these will always work, and you only need 2. So just kind of simplify it. One ray that comes in parallel to the axis, and we know where that has to go by definition. That goes right through the focal point. A second ray that we can always draw for the mirror hits the center of the mirror and bounces off so that the angle of incidence equals the angle of reflection. That's always true, but here the normal is well defined because it's the axis of the mirror. And so that makes it a lot easier to draw that. So if I've drawn these correctly, and there's always going to be a problem, but it helps to know what the right answer is. And so have them come together there. And so this is our virtual image. We'll notice here that it's on the far side of the mirror, therefore it must be virtual. There's no real convergence of light at that location. And we also see that it's about twice as big as the original source of light here, which is at the object location. And so that was the kind of thing that you saw last time when I brought this pen in. And you see this magnification effect as I bring it in, but it's still upright. And so we can look at other variations, but it's always going to be in a right side up or upright virtual image if the object distance is less than the focal length. So no matter how hard the mirror tries, it's doing the best it can, but it just doesn't have enough curvature to bring the light together to a real focus of light. Are there any questions about this case 1?
The only case where you have a real image is the only possible way to get that is with a concave mirror where the object is beyond the focal point. And
Yes, that's correct. The only way you can get a real image is with a concave mirror where the object distance is out here somewhere. That's correct. And that'll be my case 2. So this is case 1. I'm doing this as case 1 just because this is something, if you've gone to a funhouse mirror and you've stood up next to it, or you've seen what I just did here, it's a lot like what we would experience with a regular plane mirror, except without the distortion. Okay, but in case 2, I'm calling this case 1. call this one case 2, we'll put the object distance greater than the focal length. So if we do that, then let's keep the focal length at 10 centimeters. And let's put the object now 15 centimeters away from the center of the mirror. And let's see what the math does, and then let's try to draw a ray diagram to verify that the math is giving us the right answer. Okay, so again, what we're going to be doing in these problems is find I and the magnification. Those are the things that we're looking for, given O and F. Now there are other variations on this. I could give you the location of the image and have you solve for the focal length. Okay? But normally, in a problem like this, you'd have the focal length written on your mirror, and you'd be able to measure the object distance away. And so then you would be able to verify that that, in fact, corresponds to an image that could be projected onto a screen. Okay, so here we've got 1 over I equals 1 over F minus 1 over O. 1 over 10 minus 1 over 15. Again, I've chosen numbers where it's relatively easy to find a lowest common denominator. So I'll just choose 30 here. So this would be 3/30 minus 2/30 or 1/30. That's 1 over I. So then I is equal to plus 30. Okay, so what this is showing us then is that it's a real image. That means that you could put a screen there and project the light source onto the screen. Okay, so how would I, and let's do the magnification while we're at it. Magnification minus I over O. So in this case, we're going to get an inverted image. You see here that the magnification will be negative. What a negative means is that the image is flipped upside down. This would be minus 30 divided by 15, or minus 2. These are centimeters, of course, but the centimeter units are canceling, and so I'm not writing them in. And so I'm going to see something that if I projected a screen, it should be 30 centimeters away on the near side. So this would be 30, about like that. If I'm drawing this 10, 20, 30, something like that. And it's going to be a flipped upside down image. So how do I verify that? Well, again, just remember what I did last time. One ray comes in parallel through the focal point. Do the same thing here. Parallel through the focal point. A second ray can hit the center so that the angle of incidence equals the angle of reflection off of the axis. And if I've drawn these carefully, they'll come back together again at the right point. So here. These drawings can't be expected to be perfectly accurate. But they give you a sense for what's going on. This is telling me it's flipped upside down. It's real. Now, what would this mean? Well, if I put a screen here, you could project the light right onto that screen. It would be an upside down image. Okay. But if I put the screen in a little closer, it would be blurry. Because one point here would map into 2 points there. And if I put it farther out here, then the light would come together and start to spread out again. So it would get blurry again. So as I take the screen and I move it back and forth, I find that there's just one spot that gives me a clear focus. And so you've got that thing going on in a simulation that you'll do in this week's lab. And so that then is what we would call a real image. Now what about, why are we just doing it for that point on the end? Why not a point in the middle? Well, a point in the middle is going to do the same thing. It's going to reproduce this point on the image. So if I start from here, go through the focal point, then this one would come in so that the angle of incidence equals the angle of reflection. And so that point would also map out on the image. And so we're just looking at extremal values and figured that all the rest of them will do the same thing, but we'd have a hopelessly confused ray diagram if we tried to draw an infinite number of rays. You wouldn't be able to see anything. So we just draw the most extremal rays. And then if we put the screen at the right spot, then we can project the light onto that screen. Now, why would we want to do that? Well, this could be, for example, light coming in to a reflecting telescope, and then we would bring the light together, and we'd actually be using a lens also in that system in order to get additional magnification. But optical devices use these kinds of principles. Okay, so that's our case 2. Then we've got different variations of this. If we're more than twice the focal length away, then the magnification is going to be less than 1. That's still inverted. And if we're between f and 2f, then it'll be like this, where we have the magnification greater than 1. But it'll always be flipped. This is always real and always inverted. So by real then, we just mean that there's a physical convergence of light at that point. Here, this is not a real image because there's not a physical convergence of light at that point. That's virtual. This is just the eye being tricked to extrapolate along those straight line paths. Is that useful? Well, yeah, because you can magnify something and then maybe you can see it better. And there are more complicated aspects to it too. Now there's a case 2b in which the object distance is equal to the focal length. Okay, so that's between these two. Here the object distance is greater than the focal length. Here it's less than the focal length, but what if it's right on the focal length? Well, then we have something that's kind of weird. But we could probably already guess what that would be, because we know what happened when we put the flashlight bulb at the focal point of a mirror, is we got parallel rays. Parallel rays only converge at infinity, so therefore you're going to get something that has infinite magnification. Okay, so let's try to draw this and see what I meant by that strange statement. Okay, so here's the focal length, f. Here's our object, O. Put it right on the focal point. So one ray comes in, goes through the focal point. The second ray hits the center, comes off, angle of incidence equals angle of reflection. And if I've drawn these carefully, we get parallel rays. And so what that tells us is that the image distance is infinite. Because here we have 1 over I plus 1 over O equals 1 over F. So that means that 1 over I is equal to 0. Because 1 over O is equal to 1 over F. But then if we invert that and punch that into our calculator, smoke starts coming out. It says error because it's infinite. It's not a real physical number. But that's just what Euclid told us. In a flat space, parallel lines will not ever converge. Okay, and so that's our limiting case then, which is kind of halfway between it being a real image or a virtual image. Because if you extrapolate the line out this way, then the extrapolation of the rays also never converges either. So if you look through this way, so essentially what you would see then, if you put light right at the focal point, is you would see one little point on the object take up your whole field of vision. And so that's something you can play around with here. I can't quite see when that's happening, but as I move my hand in, there's a certain point where I get quite a bit more magnification, and there's a little bit of distortion in this mirror. So So you're not going to see quite where that is, but if you had a very good mirror, and you're able to hold your hand steady at just that focal length distance, one little point would basically take up the whole field of vision, because it would be essentially infinite magnification. Okay. So when you look at yourself in this mirror, you're seeing yourself upside down, right? So you might say, well, it must be a virtual image, but it's flipped upside down. No, that's not the case here. Your object distance is way greater than the focal length, inverted image real, okay? So you may think that you're focusing on a point on the far side of the mirror, but in reality, you're focusing on a point that's in front of the mirror. That's where your real image is located. It's just your mental model for mirrors is that you think you're focusing on a point that's on the far side of the mirror. But you're actually, when you see yourself in this mirror flipped upside down, you're seeing it, the light comes together like this, and then it comes back out to your eyes like this. So then you extrapolate back to a point that's in front of the mirror, and that's where you're seeing the real image of yourself as a virtual, as a inverted but real image in front of the mirror. Okay, there's one other kind of mirror that we also should talk about, and that's called a diverging mirror. The diverging mirror pokes out at you. That's called convex. So concave is crawling into a cave. Convex is the other one, poking out at you. Okay? And so when you look at a convex mirror, what you're always seeing, essentially, is a reduced right side up image. Okay, and so that, okay, so here, get rid of this. So here, notice that they're drawing all kinds of rays in here to get the real and the virtual image. I'm trying to simplify that because I don't think you need all those rays. And sometimes it's not clear which rays to draw. It depends on which situation, if you can draw some of those other rays or not. But these are the two cases we've looked at so far. But here, we've got a diverging mirror. And so what we'll see then is that light that comes into a diverging mirror always produces a virtual image. Is there any way of making sense out of that? Well, yeah, because how could a mirror that's spreading light out ever bring light together? It's impossible. Because that's all it does, is spread light out. So here, the converging. I had a diverging. I guess I don't. So I'll just draw a picture of that. For a diverging mirror, and this also brings in an important concept regarding what we call a virtual focal point. And by the way, all the math that I've been doing here for mirrors is also going to work for lenses. If we just tool up a little bit, I'm going to be showing you some lens equations that look very similar mathematically in a few minutes. Okay, so with the diverging mirror, pokes out at you. So parallel beams come in, but there's still the angle of incidence equals the angle of reflection. So that's not changed. But the curvature of the surface and the orientation of the normals to the surface have changed. So here this would go in like this, and then come out like that. And then this would be the normal at that point. Remember, everything's always measured relative to the normal. So these parallel beams come in, they bounce off, and spread out. Like that. And so if you had an eye here and you were following along, the path, the apparent path of those light rays, what you would find is that they would all seem to converge at a point. And so that's what your eye would see, is this apparent point source of light on the far side of the mirror. But as we already know, that is not possible, because light can't go through the mirror, right? It can only bounce off the mirror. And so we call this then a virtual focal point. And the magnitude of f is less than 0. Okay, so this is f. But in this case, let's make it negative 10 centimeters instead of plus 10, as we had had in the other example. Okay, and so why would we want a mirror like this? Well, what you can see when we are looking through this kind of a mirror is that you have a wider field of vision, but it's at the expense of the accuracy of your depth of perception. So sometimes on these mirrors it'll say, caution, vehicle may not be at the correct distance away, may appear closer or something than it actually is. And so when would we use that? Well, if you have, say, a big motor home or a big truck or something, and you need to have a better field of vision of cars, and you're willing to bite the bullet on not being able to tell quite where they are, but just being able to see that there's something there, then that could be useful. Also, if you are going around a steep mountain curve and you can't see around the edge of the curve, the mirror could be put at a strategic location so you could see the car sooner than you could actually see it along a straight line of sight. And so that could give you a little bit of extra time that would allow you to avoid an accident. Or if you're going up and you're popping a bunch of $20 bills out of the money dispenser at a bank, you might want to see if somebody's sneaking up on you from behind. So they put those curved mirrors there so you can see a wider field of vision. There's also reasons to do this with telescopes. In a telescope, what's called a Cassegrain focus, the light comes in like this, bounces off of one mirror, and then before it gets to a point of focus, it bounces off of a second mirror. And that allows for the light, this spreads it out, but if you have the curvature right, it still converges. It just doesn't converge as fast. So instead of it coming together here, instead the light comes together there. And so this then is a convenient viewing platform for you as an astronomer to look at the stars. So there are several different applications of this as well. What I'd like to do to finish this off is to do one example. There's not a case 1 or a case 2 for these. Okay, so let's put the object here, and let's say the object is 5 centimeters away. And let's say the virtual focal point is -10, like that. So that's where the virtual focal point is. This is our object distance. This is our virtual focal point. Now, sometimes it's useful to put the focal point on both sides of the mirror. I don't think that's really going to help us too much here. And so what I'm going to do is just draw 2 rays. One ray I can draw comes in parallel to the axis, and then it bounces off so that the extrapolation of that ray goes to the virtual focal point. We know that that is what parallel rays do. They bounce off that the extrapolation of that ray goes through the virtual focal point. The second ray that we can draw is the same one that we drew before, hits the center and bounces off, so the angle of incidence equals the angle of reflection. So if we extrapolate along those two lines, where they come together is our virtual image. So it looks upright, and it looks reduced in size. That's the same thing as saying the magnification is less than 1, but it's less than plus 1, right? Because it's upright. Okay, and so that's what you see then. When you look through this mirror, no matter how far away I am, it's still an upright image, and it's still smaller. Okay, so that's always going to be true. It doesn't have like a case 2 where you're farther away than twice the virtual focal length or something like that. It's always basically the same ray diagram. But I found that this one tends to confuse people more because they're not real clear as to what was happening. So remember, one of the rays comes in, bounces off so that the extrapolation goes through the virtual focal point. Then the second one is just that same old ray we always draw. So really, they're the same old rays that we always draw anyway, because in either case, either the ray or its extrapolation, that's the parallel ray, always goes through the focal point, or the extrapolation goes through the virtual focal point. So you're always doing the same thing over and over again. You don't get confused by which situation you're in, which ray you have to draw. Okay, so let's do the math. Surprisingly, for this kind of a mirror, you can still use the same equation. 1 over I plus 1 over O equals 1 over F. And again, the derivation for that is on the front page of this handout that I gave you. If you have any questions about that, let me know. I know some of you are interested in stuff like that. Then here we got 1 over I equals 1 over F minus 1 over O. So I know that I has to be negative because F is negative. And we're subtracting a positive number away from it. Okay? And so the whole thing has to be negative. Therefore, the image is always negative. Okay, so here we have minus 1 over 10. Don't forget the minus sign. Easy thing to forget. Minus 1 over O, that's 1 over 5. So that would be equal to minus 1/10 minus 2/10 is equal to negative 3/10. So that gives us I. Remember, we always wait till the end to flip. Don't flip in the middle. Get the 1 over I solved for first, then flip. So I is equal to minus 10/3. So that's where we're at here. That's 3.33. So if this distance is 10, then I've drawn this fairly accurately. It's about 3 of those. And so that is our upright virtual image. Let's figure out the magnification. We're going to expect a magnification that's less than 1, but positive. So this is a way you can check your results. And if it's a multiple choice question, I might give you a list of ray diagrams and say which one represents this. But otherwise, you'd just be looking for the mathematical result. But if this were a free response question, then I would definitely want to see the ray diagram too. So the m then minus I over O, so that's minus a negative 10/3 divided by 5. So that's going to be plus 10/5 divided by 3, or plus 2/3. So the magnification is reduced in size, only about 2/3 the original size, and is upright. Any questions about that?
Can you explain at the beginning how it was negative again?
How what was going to do it?
The formula with the equation just right at the beginning where 1 over I is...
Which quantity were you referring to that's being negative?
I guess the negative 1 over O.
1 over O is a negative. That's positive. The focal length is negative. It's never really coming together here at the focal point. This is not the real focal point. There is no real focal point. But if you bounce rays off of here that are parallel, that come in parallel, the extrapolation of that ray goes through that point.
Oh,
And that is, it works out in the equation to just make the focal length negative.
okay. Gotcha, okay.
And then you get the right answer. I didn't prove that here. That this is probably more than a lot of people want to see anyway, but it's all right. I want to expose you to it, and these are things that I always like to know about. I know some of you just want things that you would see on the exam, but it gives you a little bit deeper understanding into why these things exist, to see what the derivation is. Any other questions? All right. So now what I want to do is move ahead to lenses. So, if we have a lens, what that is going to do is it's going to do much the same kind of thing that the mirror did, but it's going to bring light to a point of focus on the far side of the lens, whereas the mirror brought light to a point of focus on the near side of the mirror. And what we'll notice here is that for a spherical curvature, we don't get quite the right answer. We don't get parallel beams quite coming into the center, because off near the edge, our ideal curvature for a converging lens is parabolic. And what we have instead are spherical lenses, because they're easier to make. Doesn't mean you can't machine a parabolic lens. It's just, it's way more expensive and harder to do. And so a parabola fits nicely into this part, but not so well up here. And so what will happen then is the light that comes in closer to the center of the lens will come together at the focal point. But light that comes in from farther away is what we call a spherical aberration, which is a distortion that's caused by the difference between the curvature being parabolic and the curvature being spherical. This here is the distorted one, and this is the distorted. Now, it turns out that you have the same sort of problem with curved mirrors. The Hubble Space Telescope, our original telescope that was able to open our eyes to so many things in the universe, had a spherical aberration in it. It was sent up, and they didn't actually test the optics here on the Earth, which meant that there was like $1.5 billion rescue mission where they had to put corrective eyeglasses on the Hubble telescope to fix it. And the amount of variation in that curvature between parabolic and spherical was only about 1/50th the diameter of a human hair. So it didn't seem like a big deal, but it made the Hubble telescope's eyes blurry. And similarly, we get the same kind of problem in a camera. You can get different kinds of aberrations, and you can get color distortions too, because different frequencies of light have different indices of refraction. And it's for this reason that you can take light, for example, from a and here we have the problem then with the aberrations. And you also have the color distortions. So this is another reason why really big telescopes don't normally use big lenses to gather the light. Because even if you've got the curvature identically right, then where the two light rays come together is going to be different depending on the color. It's going to be slightly different. It won't be a lot different. Then it could create some little rainbow effects. And this, by the way, is the whole thing that Isaac Newton did to... But with a prism, you can get different colors of light coming out of a prism because of the fact that different frequencies have slightly different end values. And so these are things that have to be considered then when you use a lens, because the angle of incidence always equals the angle of reflection for a mirror. But for a lens, you can get color distortions and you can get spherical aberration. So both of those things have to be accounted for. So they had, back in the time of Isaac Newton, they would have telescopes where they would have different shaped lenses that would keep the light from spreading out and try to correct for those spherical aberrations. So they were getting an arms race of telescopes. Some of them were like 150 feet long. And then Isaac Newton came up with this idea, well, let's just use a mirror. So he had this little thing that you could fit in your pocket. He was pretty handy. He made it himself. And it pulled in light as well as that 150-foot long telescope did. And so his boss at Cambridge said, hey, would you mind if I borrowed that and showed that to some of my friends? The Royal Society? He goes, sure, go ahead. And so that is still the design that's used today for a reflecting telescope. Okay, but with a lens, we neglect those aberrations. The basic property of one of these lenses is that if it's a lens that's thick in the middle and thick toward the outside, that's what we call a converging lens. So, and it does a similar thing to what the mirror does. It takes parallel beams of light and brings them to a point of focus. Why does that happen? Well, we have to use Snell's law. And so if you look at what's happening here right at the surface, let's say a ray is coming in like this. And this is your normal. And this is going to be air, and this is going to be glass. So it's going to bend toward the normal as it enters the glass, so that this angle is smaller than that angle, theta 1, theta 2. And then when it comes here, here's your new normal, bends away from the normal when it's going from more dense to less dense. So that bends it again in that same direction, so that this angle here, theta 3, is greater than this angle here, which is theta 2. And so both of those effects together have the net effect of bending the light toward a focal point. That you can work it out just from Snell's law. N1 sine theta 1 equals N2 sine theta 2, but with the different normals being associated with the different points on the curvature of the lens. Okay, so this is where it comes together then is still the focal length. If you have a negative lens, then that does the opposite, kind of intuitively reasonable. But if you extrapolate along those straight line paths, you end up with a virtual focal point. Just like with the mirror. So if you've been following what I did with the mirror, all you have to do is gear up for a little bit different definition of what's going on, slightly different ray diagrams, and the math is going to be pretty much identical to what we did for the mirror. And so that is handy, because then we don't have to relearn a whole bunch of stuff. That's a lot like with a string. We had certain standing wave patterns, and we had an amplitude. It's a function kx minus omega t plus phi. They were able to do the same thing with the pressure function. Still had nodes at the endpoints. And so a lot of times we can reuse this math in what seems like a different application, but it actually has the same kind of mathematical solution. So that once you get good with that math, then you go, okay, I know how to do the math. I just have to analyze the problem a little differently. All right, so as was the case with the mirror, we've got different case situations here. And these, I've got all of these outlined for you. Here are the lens equation. Got all these different cases on the handout that I gave you. I'm going to summarize some of that stuff here. Here, let's try a case 1 situation where O is less than F. Okay, so that's the kind of thing we were doing before. Let's say F here is equal to 10, and O is equal to 5. So that's from the center of the lens. Okay, so that's just kind of a lens here. This isn't a very big lens, but if you can see, I can make it into a magnifying glass. That was very helpful. Right here, the Expo pen. You can make it bigger. And we've done this before. Everybody's used a magnifying glass, right? Okay, so you can make it bigger. If you can't read something, use a magnifying glass. Or if you don't want to spend a lot of money for reading glasses, you just go to the dollar store and you get something that has a couple of these in it, and it kind of works. Maybe it gives you a little bit of a headache, but it works because it makes things look bigger. Very helpful. So let's look at how that kind of array diagram would look. Usually for these, I like just to get into just a general habit, I like to put the focal point on both sides. It's not always helpful, but sometimes it is. And so here I can gauge the focal length, even though the light is going to be going through the lens that way. Okay? And so here one ray is going to come in parallel. That's going to go through the focal point. Okay, so that's one ray that we can always draw. A second ray that we can always draw is one that goes through the geometric center of the lens with no net deflection. Sorry. Draw that very well. Through the center of the lens with no net deflection. Okay, so there's no deflection for the ray that goes through the center. That's why it's an easy ray to draw. You might ask yourself, well, why would that be true? Why is there no deflection if you go through the center of the lens? Well, if you take the lens on one side and the lens on the other side, and it's going through the center, then this normal and that normal are going to be parallel to each other. And so that means that the faces here are parallel. And we already know what happens if you send light rays through parallel faces. It bends, but then it undoes the bending and ends up with no net deflection. And so that's essentially what we have here. for points that go through the center is that the tangents to these two surfaces at the point of entry and exit are parallel, and so it works exactly the same way as a refractor that has parallel sides. And so that's the reason why this one works. We know why this one works, because that's our definition, that parallel rays always go through the focal point. But we can see that these rays are not coming back together. So I'm not going to be able to put a screen there and project light onto that screen. It's going to just be blurry if I try to put a screen there. But what my eyes can do is a little more sophisticated than that. What my eyes have learned how to do from millions or even billions of years, not billions, millions, hundreds of millions of years of evolution, is to extrapolate along straight line paths to the apparent source of the light. And so this is going to produce a virtual image. This is going to be upright. And it sure looks to me like it's bigger, so we would say that's enlarged. So it's going to be upright, virtual, and enlarged if the object distance is less than the focal length. And that's our magnifying glass. Let's do the math. So we got 1 over I. Again, I'm going to solve for the image distance. 1 over f minus 1 over o. That's going to be 1 over 10 minus 1 over 5. 1/10 minus 2 tenths, negative 1/10 for 1 over I. So I is equal to minus 10. So this is virtual. Now, a virtual image with a mirror is on the far side of the mirror. But a virtual image for a lens is on the near side of the lens. So even though the math is looking the same here, surprisingly, we have the same equation. 1 over I plus 1 over O equals 1 over F. And we have magnification minus I over O, just like we had before for the mirror. Same thing is true for the lens. But the interpretation is a little different. Because here, light can go through the lens. And so that means that once it goes through the lens, the eye has to extrapolate to where the brain thinks that light came from to produce this virtual image at this location. And we can see that it looks like it may be about, well, it's right there at the focal point. But it's at minus 10 because what we mean by negative here is that it's on the same side of the lens as the source of light. Because lenses can only, if it's going to actually form an image, it's going to have to be on this side, right? Because nothing's reflecting. So this is just a trick of the eye, that it's extrapolating to that point. And that's what the magnifying lens does. The magnification minus I over O again. This may look similar to another calculation I did for the mirror. That it's a different problem. Clearly a different problem. The math, though, is pretty much the same. Minus a negative 10 divided by 5 gives us plus 2. So it's twice as big, upright, and on the near side of the lens, no real physical convergence of light, virtual image. Any questions about that? Okay, the second kind, case 2, is going to be when your object is farther away than the focal length. I think we kind of know what to expect for that one. see this without turning on the lights. Can you see that?
Yes.
Oh, no, turn out the lights. So what you can see here is that this is where the screen is located. It's right on the board. And so I'm adjusting, this is all measured with respect to the lens. So the O is distance measured, thank you, Mark, measured from the lens. And then I is the distance from the lens to the screen. But notice if I bring it in too close or too far away, it goes blurry. And only at that one point is it looking reasonably straightforward. But you see here, this is an F, and that's an upside down F. So it's an inverted real image. Okay, so let's do that over here. Call this again case 2, where O is greater than F. Let's put the object distance at 15. And the focal length at 10. Now we're neglecting the thickness of the lens here in our calculations. And because of that, this is called the thin lens equation. So it's not exact because of the fact that we are neglecting the thickness of the lens. But it's close enough to give us some reasonable results. Okay, and so what I could do here then is I could calculate the image location and magnification, 1 over F minus 1 over O, or 1 over 10 minus 1 over 15. So that's 3/30 minus 2/30 equals 1/30. And so therefore I is equal to plus 30. Okay, so if this is 10, then I'm going to go 10, 20, 30. I'm expecting the image is going to be over here somewhere. And the magnification M is going to equal minus I, so that's minus 30 over O, which is 15. So that gives me negative 2. And so I'm expecting an image around here that's maybe about twice as big and flipped upside down. The negative means it's flipped upside down. Let's see if the ray diagram is going to agree with me. One ray comes in parallel, and then I'm drawing the focal point on this side. So see, I've got the focal point in reference on this side to the distance. That helps me draw my diagram. And then one of these rays goes through there, and then continues on. Then the second one goes through the geometric center with no net deflection, and also ends up at that same location. So this is our real inverted enlarged image. And that's just like what I did a second ago when I projected the light from that F onto the screen. The location of the screen would be here. So if you put the screen in too close, we put the screen in far away, then it goes blurry, which is just like what you saw. Any questions about that? Yeah. Huh? It's twice as big and flipped upside down. So that's what we got here. This is about this distance, that's about twice that distance, and turned upside down. Just like that big F that we saw that was up on the board. We had a smaller F. But it's not always going to be bigger. It depends on how much farther away we are from the focal point. If you get more than twice the distance away, then the magnification is smaller, less than 1, but it's still negative. So it'll always be inverted, and it'll always be real, but it won't always be enlarged. And when you're at twice the focal length away, then the size of the image is the same. Okay, so that's the crossover point. If you go from f to 2f, then it's bigger. But at 2f it's the same, then greater than 2f, the image size is small. Okay, so that's all I wanted to do with this. We got a quiz to do, so I'll go ahead and put some of these quizzes out on the side when you're ready to